Welcome to the welcome to the third webinar in preparation for the Grassroots Nuclear Waste Summit on nuclear waste, which will be in early December 2016. This is the third in 3 of our preparatory webinars. This one is on high-level radioactive waste, irradiated or spent nuclear power fuel, aging fuel, high burnup fuel, the characteristics and dangers of storage in pools and in casks, hardened on-site storage, and a little bit about the problems with reprocessing. We have 2 presenters tonight, Gordon Thompson, who is the Executive Director of the Institute for Resource and Security Studies in Massachusetts, and Donna Gilmore, who is the founder of San Onofre Safety, an organization near the San Onofre nuclear generating station, which is now closed in Southern California. Gordon is an engineer. He's got his degree in engineering and science, got his doctorate from Oxford in 1973, has been based in the U.S. since 1979, and one of his major areas of interest is the impacts of nuclear technologies and the opportunities to limit those impacts. Donna is Donna's organization is San Onofre Safety, and her website, sanonofresafety.org, is used around the world by journalists, engineers, elected officials, regulators, and the general public as a credible source for information on nuclear safety issues. She's done a few papers, including High Burnup Nuclear Fuel, Pushing the Envelope, co-authored with Dr. Resnikoff, Diablo Canyon, Conditions for Stress Corrosion Cracking, and several others. So the webinar tonight is focusing on irradiated fuel, which is the hottest part of the nuclear fuel chain from both nuclear power and weapons. In the U.S., we've got categories of waste, high-level, low-level, so-called transuranic, mining and milling wastes, and then the government would like to deregulate some of the waste and declare it not even radioactive, although it is. So tonight we're focusing on the high-level radioactive waste. Uranium, when it's in the ground, is not that concentrated, so it is mined, making enormous amounts, leaving enormous amounts of waste. There are several isotopes of uranium. Uranium-238 is the highest percent, and uranium-235, which is the lowest percent, is the one that's needed to make nuclear power and nuclear weapons. So the uranium is mined, it's milled, it's processed, it's formed into fuel pellets, which are very tiny, and then these pellets are stacked into rods that are assembled into bundles or assemblies, and several hundred of these go into the core of nuclear reactors and fission. The uranium-235 is split, fissioned. Its binding energy turns the turbine, heats the water, which turns the turbines and makes electricity, and the fuel itself and the assemblies gets clogged up with fission products and activation products and transuranics. So the uranium, when it first starts out, could be held in your hand, but by the time the fuel assemblies come out of the reactor, they are millions of times more radioactive. The industry, government generally call it spent or used nuclear fuel. We refer to it as irradiated fuel because it is millions of times more radioactive when it comes out of the core. And in fact, nuclear power fuel, fuel from nuclear power reactors, really has about 99% of the radioactivity in the whole nuclear power and weapons fuel chain in those assemblies, and then sometimes it is reprocessed. The U.S. does not reprocess now, but Gordon will talk about that a little bit, but reprocessing actually makes the problem worse because they chop up the assemblies, dissolve them in chemicals, and extract the uranium and plutonium, leaving the all the other radioactive elements, cesium, strontium, iodine, neptunium, others, to in a liquid and sludge. So the problem then is more difficult. So we're focusing tonight on the irradiated fuel that comes out of the reactor core. And we can move to Gordon. We'll have Gordon Thompson now tell us a little more about the storage and management of that irradiated or spent nuclear fuel after it comes out of the reactor core. It stays in the core. It stays in the core for maybe 2, 3, 4, 5 years, and then it is moved into fuel pools. And this is all done remotely because it would give a lethal dose in just a few seconds if people were exposed unshielded.
So Gordon, we're transferring over control of the screen to you.
Okay.
It'll be.
Can I click on share my screen?
Yes, there you go. If you want to put your
slides
in, yes. If you want to put your slides in display mode, then you're ready to go.
You want to tell them how to do that?
Okay. How's that?
It looks. Your notes are showing, or your notes your note.
Ah. Well, because on my screen it's in display mode. So
you could move the pictures on the left. Yeah.
try that one. How are we doing now?
Looks the same. Let's see.
Now it's not showing.
On my screen it's in display mode, but I guess not on yours.
No.
I don't know how we fix that. Do you have it up on your machine? You could display it?
Certainly, yeah. Yeah, we could show it from here.
This will be my January 2014 slides.
Okay.
You have it?
Yes. Yes, I do. I think I have it queued up right now.
Okay. And I'll just tell you when to advance.
Okay. Can you see what I'm displaying now, Gordon?
Yep. Okay. So we're good to go.
Yes. Oh.
Okay. Good evening, all. My name is Gordon Thompson. Let's stick with the title slide for now. I've given a lot of talks on this subject over the years. I'm using here the slide deck from a presentation to the commissioners of the Nuclear Regulatory Commission in 2014. This was an unsuccessful presentation to attempt to persuade the commissioners to authorize the expedited transfer of spent fuel to dry storage and the removal of the fuel from high-density storage in pools.
Gordon, could you speak just a tad louder, please?
Sure. How's that?
Excellent.
Okay. Slide 2, please. This picture on the right shows a rack for the storage of spent nuclear fuel. And Diana's just given you a good quick rundown on what spent fuel is, or irradiated fuel. Back when nuclear power plants were first designed in the 1960s and 1970s, it was thought that their spent fuel or irradiated fuel would be taken away for reprocessing. So the spent fuel pools were equipped with low-density open-frame racks. The one shown is for pressurized water reactor fuel, and boiling water reactors have a somewhat different arrangement, but I'll focus here on the PWRs, which are the most common type of reactor. This rack design had the virtue that it was inherently quite safe. Criticality, that is nuclear fission, was suppressed by the geometry, by keeping fuel assemblies spatially separated. And if water were lost, the fuel would be cooled by circulation of air and steam. This is significant because nuclear fuel is clad in tubes of zirconium metal. Zirconium is a metal that's chemically extremely reactive. It will react with air or with steam, and if it reacts with steam, it produces hydrogen gas which can explode. This has been known for many, many years, but the nuclear industry has used zirconium because it has good properties in terms of standing up to the very harsh conditions in a reactor and of not absorbing neutrons, and thereby allowing the fission process to proceed. When reprocessing was stopped, which became formal in the Carter administration in the mid-1970s, spent fuel began to accumulate at power plants. And the nuclear industry could have accommodated to that situation by building additional spent fuel pools at reactor sites, by taking the fuel away to other interim storage sites, or by going to dry storage. Instead, they took the cheapest solution, which was to switch from the open frame racks we see in the picture to high-density closed frame racks. The racks are closed because to suppress criticality, it was necessary to have plates of boron-containing material between each fuel assembly. That created a very severe accident potential which continues to exist today. And that potential arises if a pool loses water for any reason. Next slide, please. And this is an array of circumstances whereby a pool could lose water. And at the Fukushima unit number 4, the top left mechanism, sloshing, was significant for two reasons. The first, earthquake caused sloshing of the fuel, and then the hydrogen explosion that occurred later in the accident also displaced water. So about 1.5 meters of water was lost from the Fukushima number 4 pool through the sloshing mechanisms. Water was lost over time by boiling from that pool. That's the second from the bottom. And there was leakage. Fortunately, the leakage at Fukushima number 4 was into the pool by very fortuitous chance. And the outcome could have been much more severe if there had not been that inward leakage. The staff of the NRC considers only the modes with the red asterisks, and only for earthquake initiation. So the majority of scenarios for water loss they simply don't consider at all. Next slide, please. This is the worst situation that arises if water is lost from a pool, and I've termed it the severe reference case. And that's where there's a residue of water in the bottom of the pool, and that residue of water prevents circulation of air, meaning that the upper portion of the fuel assemblies are cooled only by steam. As I explained earlier, steam will react with zirconium and produce hydrogen. We actually have had an experience like this at a small scale at a plant in Hungary in 2003, the PAX-2 unit. Fortunately, that occurred in a closed vessel, but it proved the physics of what I'm talking about. Over all the years that this fire potential has been an issue, the NRC has consistently refused to study this severe reference case. So the the most important case, the worst case, is the one that they simply refuse to consider. Next slide, please. Now, if water is lost from a high-density fuel pool, the zirconium cladding doesn't start burning right away. There's an ignition delay time while the fuel heats up to the ignition point. And if the fuel is aged 1,000 days or roughly 3 years, you're looking at a day or a bit less for the fuel to heat up and catch fire. So many people in the industry and in regulatory bodies like NRC say, well, no problem. If this situation ever arises, we'll just rig a bunch of fire hoses and spray water on and everything will be fine and dandy. And they do actually have now, post-Fukushima, additional capabilities to do that. They have more portable pumps and fire hoses for cooling purposes. However, they have neglected a very important matter, which is shown in the next slide, which is that a reactor release could contaminate the site such that approach to the site would be impossible due to the extremely high radiation fields. And the numbers shown indicate just how high those fields are and how impossible it is for any human to approach. And this is extracted from testimony I gave in the year 2000 that was disparaged by industry and by NRC witnesses in that case. It was to do with the Harris plant in North Carolina. The Fukushima incident of 2011, of course, proved the point that I had been making back then in 2000. And you may recall, those who were watching television at the time, efforts to drop water from helicopters into the spent fuel pools. And eventually a concrete pumping truck was brought up to the site and did succeed in adding water, although not terribly effectively. And as I mentioned, leakage into the pool was actually the saving factor in that incident. Next slide, please. So what do we have to worry about here? Cesium-137 is the key isotope to worry about. It has a 30-year half-life. In its decay, it produces a very intense gamma radiation. And the amount released at Chemobyl in 1986 was approximately 85 petabecquerels of this material. Petabecquerel is 10 to the power of 15 disintegrations per second. It weighs about 300 grams. You could hold it in your hand, but you wouldn't live very long if you tried. The fact that such a small mass produces such dramatic effects is instructive about the hazard of nuclear power. Best we can tell, at Fukushima, about 6 petabecquerels fell on Japan out of a total release that has varying estimates. The one I'm quoting is 36 petabecquerels. There are still ghost towns in the Fukushima fallout zone. I was actually in one about a month ago, a deserted ghost town, Tomioka. Now, potential releases, the NRC has considered the release of 330 petabecquerels from the Peach Bottom plant and found that about 4 million people would become long-term internally displaced persons. and that is displaced essentially for the foreseeable future in the most contaminated areas for several hundred years. The French Research Institute, the RSN, looked at a potential release of 100 petabecquerels at the Dampierre site in France. This is a reactor release, and concluded that that would be, in their words, an unmanageable European catastrophe. So how much is available for release? Next slide, please. Beach bottom, 2 pools, each with more than 2,000 of these petabecquerels. And Fukushima Unit 4 pool, about half that much. And the ghost towns in Japan that I was visiting comes from a release of 6 petabecquerels. And of course there are many, many acres of waste dumps of contaminated soil that the government is piling up in the Fukushima zone. A single dry cask in this last radioactive case is a little under 70 petabecquerels. Next slide, please. So the NRC refused to act on this problem because they say the risk is low. And they define risk as the product of probability and consequences. Under the claim that that's a scientific definition, I regard as ideology, and testified to that effect to the commissioners who were not persuaded. Both probability and consequences are difficult to estimate, particularly probability. If deliberate action is possible, then it's exceedingly difficult, potentially impossible to assign a probability. And at the bottom, I point out that, as I said earlier, the NRC has refused to consider the most serious case. They made an assumption that the only safety issue was rapid instantaneous loss of water from the pool. And it's remarkable that they made the same error back in the 60s in terms of reactor design, focusing on something called the large break loss of coolant accident. And that's why we have such badly designed reactors and containments, because they made a similar error in the 60s. Next slide, please. Here's Unit 4. As I described, the pool is in there somewhere. You'll see the concrete pumping truck on the left. Next slide. And switching to open frame racks, to do that, we'd have to transfer fuel to dry casks. Donna's going to show you lots of pictures and talk about dry casks. The spent fuel is going to have to go into those anyway. You can see this happening at plants all across the country, and at decommissioned plants like Maine Yankee, the dry casks are all that's left on the side. And the cost of this transfer is actually simply the cost of money, the incremental cost of doing it now. So the cost is scarcely an issue, and the potential consequences are vast. Next slide. And this is the final slide. I'm saying here that the commissioners should scrap the studies done by the staff, the NRC staff, and that's true of similar regulators elsewhere in the nuclear industry have never done an open science-based inquiry into the hazard I've just described. But that hazard exists in many places. There's a major example in France of the Le Havre reprocessing plant. So if, and that's on a personal note, I first became aware of this problem in 1978. testified to that effect in Germany in 1979. My findings were accepted, and the state government at that time refused to permit high-density storage of spent fuel at the Gorleben site. So I've been pushing on this issue for now 38 years, and have never encountered on the part of industry or regulator a scientific response. So if anyone tells you this is a fast-moving, cutting-edge, science-based industry, I can tell you from personal experience that it's anything but. Thank you. And
Thanks. I should also have mentioned that Gordon has been an expert, provided expert testimony and comments to the Nuclear Regulatory Commission on behalf of a lot of our public interest organizations in the past. And we thank him for all that service and that work. Now we're going to move to Donna Gilmore. And Donna, do you want to try to make your slides show?
Okay, your screen is showing now, Donna.
Okay. All right. Donna is going to talk to us about the dry storage. Gordon has described the problem with the storage in pools, the danger of pools, the possibilities of fires and loss of coolant and all of that. And if we move from the frying pan to the fire, from the pool to the casks, what are we in for, Donna? Donna, are you there? We got her audio in?
I'm sorry, I had it on. Yes, I agree with Gordon that the pools are dangerous and we need to move to dry storage. Unfortunately, the nuclear industry has had such low standards, and they've been hiding this information from the public, that they're putting it in thin-walled, mostly half-inch thick stainless steel canisters that cannot even be inspected on the outside or inside or outside. Can't be repaired, can't be maintained, and have no monitoring system that would prevent radiation leaks. I learned this just in 2014. That Diane Curran was looking for volunteers to listen to a NRC meeting about dry casks. She thought it would be useful, and I was shocked. It was unbelievable that the NRC would allow this lethal waste to be stored, when they couldn't even inspect it. And then they said, well, they know they can have cracks. They were focused on stress corrosion cracks caused by a marine environment, but numerous things can cause these cracks. They admitted in an August 5th public meeting that once a crack starts, they don't know when that'll be, that the crack will grow on its own through the wall of the container, and it can grow in 16 years through the container. So what we're being asked to do, we wouldn't accept in a car. It's like buying a car that can't be inspected, repaired, maintained, and doesn't have a warning system to warn you it's going to fail. So when you're explaining this to people and they're reluctant to say a city council to sign a resolution or anything, just put it in terms of a car. I mean, wouldn't you expect if you're to at least be able to inspect, repair, and maintain or prevent a leak just like a car? Elected officials don't feel qualified to make recommendations for dry storage, but we successfully convince them to sign resolutions for these basic requirements. So that's a suggestion there. Now, what was even more shocking is the Coburg nuclear plant in South Africa. It leaked in only 17 years with cracks that were deeper than most canisters. There's very little operating experience, really, for the spent fuel canisters, because the thin wall ones haven't been used that long. So the NRC looked for similar components they said were comparable. And they've been trying to hide the fact about this Coburg plant, so please share it. Also, the NRC thought it would take 30 years before canisters were cool enough that salt would dissolve on the canister and start the corrosion cracking. But then they hired EPRI to check the temperature on a few canisters, and at Diablo Canyon, a 2-year-old canyon was already cool enough for the moisture to degrade the salt. EPRI is, which is a utility lab, they're even trying to hide this information. Below the left is a picture. You can see the men working. That's an air vent. The thin canisters is inside, and because the fuel is so hot, they have to have air vents in the concrete outer overpack cast there, you know, in order to cool it. And it's cooled by convection cooling. So if that thin canister was to leak, you got a nice convection cooling that can distribute any airborne gases. And then on the right is some of the highly corrosive salt they found on the Diablo Canyon canister. We even have the president of Holtec that makes and sells these canisters admit in a public meeting that it wasn't practical to repair it, even if you could find the crack. He said it just introduces another area for corrosion. And he said you would have millions of curies of radiation coming out of the canister with even a microscopic through-wall crack. The link there is to a video of him making these statements at a Southern California Edison public meeting. Now this was a chart created by Robert Alvarez for San Onofre. It'll give you a sense of perspective here. You'll see the difference in curies of cesium-137 between a nuclear weapon, the Chernobyl accident, atmospheric nuclear test. The next two bars are the San Onofre spent fuel pools, and then the last one is the 50 canisters that are currently in dry storage. So I refer to these as Chernobyl cans. Let's see, come on, page down here. Oops. Okay, now I don't like to find problems without having recommended solutions. So I did a lot of research and talked to a lot of professionals, and basically most of the rest of the world is using canisters that don't have the problems of the canisters that we standardize on the U.S. The thick walls are 10 over 19 inches. The Arriva thick casts are the 10-inch, and then the Germans have a ductile cast iron, which doesn't become brittle. They're up to actually 19 3/4 inches. The thick casts don't crack. They're maintainable. You can get close to them to do repairs and inspect. They have metal seals, double metal seals, double lids. You can inspect inside and out. The early warning monitoring is continuous, and it's a type of monitoring where you can prevent leaks. They have pressure sensors in between the seals, and if there's a pressure change, that's an indication they may need to replace a metal seal. On the thin canisters, they don't have the ability to do that. They have temperature sensing, but that's not going to give you any warning to be able to do anything. And they're only required once every quarter to check radiation levels. Somebody walks around with a monitor on a stick to check radiation levels. The thick casts have American Mechanical Standard certification on the container. The vendors will tell you they have ASME certification, but they don't have it on the container. They have it somewhat at the plant, but not for all things. The NRC gives them exemptions from ASME all the time from various pieces. Regarding defense and depth, there's lots of redundancy in the thick casts. The thin ones, it's really the only thing preventing the leaks is that 1/2 inch thick stainless steel canister. That's it. The thick ones don't need concrete, so you don't have any issues with the concrete degradation issues. They don't have the air vents that have to stay clean. They don't have the issue of wind potentially reducing the thermal capacity. I'm getting too technical now. I'm going to back off here. The thick casks in other countries are stored in concrete buildings for additional environmental protection. There's a few plants that have, in the U.S., that have thick casks, but they just leave them out. They don't put them in buildings. Regarding gamma and neutron protection, in the thin canisters, you need the concrete overpack or cast. For that, in the thick cast, you don't need it. And regarding transportability, regarding transportability, if the thin canisters crack, you have to take the thin canisters. Hold on a second. You have to take the thin canisters and put them in a thick transport cask. But if there's even partial cracks in the thin canisters, they're not approved by NRC regulations to transport that. In the thick cask, the cask is designed for both storage and transport. So the market leader in the U.S. is the thin canisters. Even if the vendors wanted to sell their thick casks, unless the NRC raises their minimum standards with these requirements, they'll never win a bid. So it's on us to expose the problems with these thin canisters, so we can get the requirements raised. I have found that people at least the highest levels I've gotten to aren't even aware of this. I met with former Chairman McFarland. She did not know these canisters could not be inspected on the outside. I met with DOE Assistant Deputy John Kotek and his Chief Deputy over the nuclear fuel cycle. He's a nuclear engineer, formerly on a submarine, and he thought he knew all about this stuff until he talked to me and I gave him the evidence. They absolutely did not know this. He kept saying to me, well, it has to be, it's required, it has to be inspectable, it's required. I mean, he was just shocked. So I feel like we have to get higher up than we've been getting because the truth is being blocked from the people that actually could turn this around. Come on, go to the next slide here. Okay, now the Fukushima used thick casks. They're about the 10-inch ones, and they stored them in a building. In Germany, they use thick casks in buildings. They've been in use over 40 years. When the industry talks about how many decades we've been storing dry storage, the ones that have been used the decades are the thick ones, not the thin ones. And when they say that they haven't had any problems, they don't know if they've got problems because they can't even inspect the outside. So yeah, they're right. They're not aware of any problems because they can't see them if they're there. Okay, and I tried my best with Mark Lombard. He's the director in charge of approving all nuclear waste canisters for storage and transport. I made a presentation, he invited me to make a presentation, and well, just like with Gordon, you know, it's hard to make progress with the NRC. So they're ignoring regulations. They know the transport regs, yet they continue to approve these thin canisters. They know the Nuclear Waste Policy Act requires monitored retrievable storage. Mark Lombard personally told me, oh, that's the DOE's problem. He's just ignoring it. They've got this new Reg 1927 Revision 1 document where they've added aging management, but they don't put anything specific enough. They say a canister that has a 75% crack has to be taken out of service, but it's impossible to even do that. They've got no path to do that, but they don't talk about that. Regarding when they lice canisters initially, they ignore anything that might happen after 20 years in their approval, and I have this in writing. And you know, I asked Mark, I said, Mark, now that you know the fuel has to stay on site indefinitely, why don't you raise your minimum storage standards? And because he knows the problems, and he says, well, it's NRC policy, you know. And I said, well, who set that policy? And then he told me he did. And he said that, you know, this way he can get the vendors to pay for the research and development, and, you know, they'll even pay for my staff's time in meetings. He actually said this. The NRC also allows empty pools to be destroyed, even though the waste is there, and it's the only way that we could possibly deal with failing canisters or retrieve fuel. It's never actually been done, but that's the only process they have that's approved. And the NRC ignores the risk of high burnup fuel in storage and transport. Now, high burnup fuel is over twice as radioactive, over twice as hot, and unstable in storage and transport. High burnup fuel is basically fuel that's been enriched with a little more 235, and it's allowed to burn longer in the reactor to make them more money. Unfortunately, it can cause the zirconium cladding to become brittle. And you know, Marvin Resnikoff, and I've done the report we did, he said that it becomes brittle, it can shatter like glass. So in transport, this could be a really big issue. Can you just see it going across the rails? The NRC is having, I forget which lab it is, do tests to see how much shaking the fuel can take, you know, so they're still researching it. Yucca Mountain was never designed for high burnup fuel. High burnup fuel can damage cladding after the fuel is already in dry storage, but because they're welded shut, we have no idea what's going on. Per Peterson, who is one of the nuclear engineers on the Blue Ribbon Commission, our California governor, looks at him as one of their gurus. He did not know that high burnup fuel could cause cladding damage after they were in dry storage. So I was able to inform him that he and Marvin Resnikoff and I informed him of that, and I gave him a reference, and so he now agrees with that since he has the reference for it. Another thing that's come up recently is Japan has outlawed aluminum alloy fuel assembly baskets. In that earlier picture, the first picture you saw all these holes in the canister. Each one of those holds a fuel assembly. Each assembly has a whole bunch of uranium rods. And the point of the basket is to keep those rods separate so they don't crash into each other. Well, we've got a problem where the aluminum basket's not going to last. I didn't think it was going to last 60 years. I've asked Mark Lombard about this because we use aluminum basket, and you know, and he said he'll get back to me, but I haven't heard from him in about a year on that issue. So they know about it, but they're ignoring the problem. The NRC approved one high burnup transport cask. They have some regulations or guides that talk about all the risk of trying to transport high burnup fuel, but yet they approved the transport cask. I read, it was an AREBA one, and I read it looking for how they possibly justified transporting high burnup fuel. They made the entire sections about that proprietary, not even one word. So we have absolutely nothing in writing for the public to see on how they could justify that. In the burnup levels, they just keep approving more and more. They've separated regulations from approvals and fuel from reactors. They don't even consider the impact on storage and transport when they approve new fuel types and higher burnups. The high burnup fuel creates hydrides. The higher the burnup, the more hydrides. There was a study where they actually took samples of real rods, high burnup rods from various reactors internationally, and this chart shows them all plotted. What's interesting here is the NRC considers high burnup 45 gigawatt days per metric ton. You can see that on the bottom of the chart. But look how about 30, 32, 35, the oxide thickness on the fuel, look how quickly it shoots up. So, and high burnup used to be defined as about 35, and they keep changing. They've changed the definition on it. So, the industry says they don't have any real data, only experimental data on high burnup fuel impact, but they do, and this was a study with the actual data. Now, there's another chart I don't have here that correlates the amount of hydrides with this oxide thickness. Now, locally here at San Onofre, we've been trying to fight the thin canisters here locally at the state level. Our coastal commission, I was able to educate them with the problems, but they gave them a permit anyway. But they want them to say, okay, they understood the problems, but you just have to promise to fix these in 20 years. So it's pretty nuts. And then Edison decided to go with this Holtec UMAX system, which is even worse than the other ones. And they're using a design that isn't even matching the specs. Anyway, I don't want to go too much into this, but if you come to the event, we can go into more detail about this problem. But look at Holtec's warranty for this great new wonderful system. 10 years for the underground structure, 25 years for that, and they want to take our existing horizontal thin canisters and store them vertically in this Holtec system, which is a whole nother can of worms. But this will give you an idea of what we're faced with here at San Onofre. You can see the canisters. They were supposed to put these Holtec canisters below ground, but they hit the water table about halfway down. So they just stuck them halfway. They're sticking them halfway down and then piling dirt on the side. And you can see where the ocean is. And that seawall in the picture, Edison wrote to the Coastal Commission and said, well, they haven't been maintaining the seawall, so we're not taking any credit for it being there. But they sure, don't tell people that. You have to really hunt for this information. Now, when are your canisters going to leak that are near you? Well, most canisters have been installed the thin canisters installed less than 10 years. A few are a little older. I've listed the oldest ones here. There's a report by state where you can see how long your canisters have been loaded in your state and some other information about them. There's other reports available at sanonofresafety.org, such as damaged fuels, and I'm hoping maybe people in New York and Illinois can make some hay with the damaged fuel assemblies they have. They have a record number of damaged fuel assemblies in New York and Illinois. This data is from the Department of Energy. Now, what about consolidated interim storage? New Mexico, Texas, and DOE plans, they're really planning the same system. They've taken the existing cans that are loaded, and they already have cracks, can't repair them, and they're just planning to take those. They're not going to have a pool. So they're assuming nothing's going to go wrong. They haven't addressed the transport infrastructure problem. These basically are so heavy they're going to have to go by rail. There's a letter that the New Mexico governor wrote where she said she was okay and one of her communities wants a facility since these are perfectly safely stored, and that's right in her letter. And there's, the same inadequate aging management plan. And, what's the point of moving these to a new location and, just taking these serious transportation risks and loading and unloading risks, if there's no advantage. I've been trying to get the local citizens here focused on the quality of the canisters. But once Edison has been giving them this hope that we can just get this stuff out of here, and a good percentage of them, that's all they care about. So it's really tough to get everybody on board with fighting for better containers. And the proposed bills they're supporting, a lot of people are supporting. If you look at what's not in the bill, it's replacing the Nuclear Waste Policy Act. It's eliminating the few safety requirements in there for monitored retrievable storage. Recommendations, we need to get this information out, and I won't go, this is kind of the, okay, I guess I'll go ahead and read this. We need to have higher standards. If we can start with city councils, counties, or the highest level we can get to have these minimum requirements that anybody can understand, to be inspected, maintained, repaired, and be able to continuously monitor to prevent radiation leaks. That should be part of the design. And I think we can do that. One of the problems is I don't think I've gotten high enough in the chain to the people that are really making these decisions. Has to be above the NRC. And we need to have them stop destroying the pools. They assume nothing's going to go wrong, and I have the documents they're using to base that on. And that's something else I can talk about at the larger session. There's so many problems with those documents, it's a joke. We need canisters that don't crack. We need to include the HAWS, the hardened on-site storage safety security standards in there. And we need to stop installing these thin canister systems and stop making more waste. I made a cost-based case with the California Public Utility System, showing that the thin wall canisters will actually cost more because they will not last as long, and there's no decommissioning money for that. The judge ruled that I made meretricious arguments, which meant I legally made my case, but she said, oh, it's not their jurisdiction, which it really is, because cost is strictly a state issue. And while on site, and this is be part of a resolution to select the best temporary location at the site, such as away from areas for coastal erosion, and in the best quality. And I have, when these slides get posted, I have additional slides after this that I won't present here, but hopefully they're self-explanatory and you can see more details.
I do believe we'll have the opportunity to post additional slides, and I've got an additional slide presentation that was presented by Bob Alvarez a couple of years ago on this same topic that we'll simultaneously post. Thank you both for your presentations. We're now going to open up to questions, and Tim's going to give us instructions on how people can ask questions. We see a few people have already started.
Okay, great. Thanks, Dee. So yes, if you want to ask a question, you can either do it verbally over your mic or phone, or you can do it by writing a question, and we'll read it off, and we'll intersperse oral and written questions as much as possible. If you want to raise your hand to ask a question orally, if you look to the GoToWebinar panel on the right-hand side of your screen, you'll see a button with a yellow hand on it, and you just push that, and we'll put you in the queue. If you want to type your question, in that same panel on the right-hand side of your screen, there's a box for questions, and if you click into that, you can type it in and then send it to us, and we'll ask it. So with that, we're going to go to some written questions that have come in, and we'll keep looking for folks who are raising their hand to ask oral questions.
The first one's from Carolyn Treadway. Where is Peach Bottom? One of you mentioned it. Where is Peach Bottom?
Pennsylvania.
And it's how many units do we know? Peach Bottom reactors near Philly?
Peach Bottom is within 50 miles of Philadelphia, It's a they're two operating reactors that are large boiling water reactors, and there's a closed third reactor which was operating in the 60s, but it's been closed for 30 or 40 years.
The next question is if we could bring up Gordon's last slide. Linda Lewison has a question that she doesn't understand, so we're going to have to unmute her for that. Can you do that?
If Linda will raise her hand, I can unmute Linda to ask her question. And in the meantime, we'll go to Gordon's slide and pull that up.
Linda, do you see the place to raise your hand? You have to click on it on your screen, and then at that point we can unmute you. I'll just unmute her.
I'll try to unmute Linda. Linda, you should be unmuted if you'd like to ask your question. But absent that, why don't we go on to the next question, and we can come back to this one when the time's right.
We have a note from Kevin Camps to Gordon. I read your expert testimony from the Nuclear Regulatory Commission Nuclear Waste Confidence Proceeding. You addressed the risk of a dry cask's contents being ignited as by a terrorist attack. Could you describe that risk some more, and also how to defend against it, a la robust storage from 2003?
Okay. Just before I start, I stopped using the word terrorist quite a few years ago because it's an emotionally laden word, and I prefer to use more objective words like adversary or attacker. And this is not a trivial point because I think our national and homeland security have been warped by an emotional and not a rational response to terrorism. The reason that a pull fire could occur is that the fuel is recently discharged and is producing a lot of heat. And if you drain the water, the fuel heats up to the ignition point and burns with either air or steam, and that can produce a runaway reaction. In a dry cask, the fuel is older and it's surrounded by helium in normal conditions. If you breach the cask, the helium will be released, but typically the fuel will not heat up to anything close to the ignition point of zirconium. In this case, it's a zirconium air reaction that you fear. The process, the attack itself, could cause a particulate release, high burnup fuel being more likely to produce particulates. However, a well-informed and skilled attacker could use incendiary material to ignite the zirconium. And in the right conditions produce a self-sustaining runaway fire of the zirconium inside the dry cask. And it's the fire produces a big cesium release because cesium is a volatile element, boiling point in the range of 600 to 700 degrees Celsius. So the concern there is a skilled and capable and perhaps lucky attacker. So I hope that clarifies.
Well, actually, this raises for me, this is Diane, a question. As you were presenting, Gordon, you mentioned that under certain situations, scenarios, that there could be a criticality. Perhaps if you could describe what that means and why we don't like those.
Well, reactor fuel is meant to go critical in order to produce fission in the reactor core. And in the reactor core, the fuel assemblies are cheek by jowl, right up against each other. And when the fuel is placed in a pool, if you put it in the same configuration, you have the potential for criticality, i.e. a fission reaction occurring. And that's why in a high-density pool there are neutron-absorbing plates containing boron, which is a neutron absorber, between the fuel assemblies. And that, in turn, is what creates the fire potential if water is lost. There are circumstances where criticality incident in a pool is conceivable. I've given testimony on that issue. It is something that deserves consideration. It's only if it were associated with or led to a fire, a pool fire, then it would be a disaster of the worst magnitude. Absent the fire, the radiological impact would be much less than for a fire.
Okay. So the next question on the that has been written in is that how it is? It just says to open frame prep. Is there beginning?
Yes, this is Linda Lewison's question. She's asking in regard to your final slide, Gordon.
Yes.
She's quoting where it says to open frame racks, and she asks, "Do you mean to keep rad waste in pools as opposed to putting it into dry casks?"
No. We have a reality that reactors are operating and they're producing spent fuel. The spent fuel has to be stored in a pool for some number of years before it can be transferred to a dry cask. So until every reactor is shut down, we will have to have pools. And what I'm saying here is that for those pools, the storage should occur in low-density open frame racks. And all other fuel should be in dry storage. And I think Donna is absolutely right to criticize the thin-walled casks. It's yet another example of cheaping out. That's why we have the pool fire problem, because high-density storage was the cheapest option, and that's why we have thin-wall casks. I hope that clarifies.
So the next question is from Connie Klein in Ohio. Are you recommending thick-walled canisters going forward, since there would be no means to transfer fuel existing currently in the thin-walled canisters? Thanks to everyone.
I assume that's for Donna?
Yeah, well, no, it can't just be, unfortunately, for going forward. I'm sitting 5 miles from San Onofre. They've been loaded there since 2003. Yeah, they have the same time frame as Coburg. I'm looking at 4 years before the could start leaking. We don't know if they will. We just know the conditions are there. And so we have all these Chernobyl cans around the country. They're like ticking time bombs. So they're going to need to be dealt with. Those are the most urgent problems in dry storage is the time they're in service. The NRC says they're going to be able to find a way to inspect it. There's no technology that's going to be adequate to do that thoroughly. They have no way to repair. A big concern I have is, ideally you have an empty pool that you're dealing with to unload. There needs to be some analysis done on that whole process. But we have an urgent problem that needs to be dealt with. And maybe we should even start with New York now that we know somebody's really caring about Manhattan. That's of somewhat importance in January. Maybe we could get a new administration's attention so we can save Manhattan.
The next question is from Kevin Camps, and he's asking, what about the risks of quality assurance violations with both design and fabrication with Holtec casks, as revealed by whistleblowers Oscar Shirani from ComEd and Exelon and Dr. Ross Landsman, NRC Region 3? Doesn't this make the thin-walled cask problems even worse because they're essentially defective in addition to their inherent weaknesses as you've described well?
I know the German thick cask, they have ISO certification, which means you have a separate independent institution, whatever, come out and independently inspect them. I brought this up to Dr. Singh, Holtec president, and I said, you don't have ASME certification, you don't have independent, you don't have what's called an M3 stamp. And he says, oh, well, we inspect the canisters ourselves, and we do a better job than they do. I mean, just total BS. But yeah, Kevin is right. But I think that the problem is probably with more of them. TVA had a situation where they caught Holtec indirectly paying a bribe to the person at TVA that was letting the contract. The person turned a witness, and how that ended up going was Dr. Singh or Holtec paid a quote-unquote administrative fee of millions of dollars to TVA, and he initially was stopped from doing business with the federal government, but after they got that administrative fee, somehow he was given permission again to sell canisters to the federal government, and TVA bought canisters from them. But yeah, Kevin's right. That's a real problem.
Okay, I just want to let Donna and Gordon know that there are about 6 or 7 questions in the queue, so, and then we've got about 15-20 minutes, so just to be aware of that in the answering. And we have Vic Mack. Did you want to raise your hand again? We missed the chance to unmute you. Actually, you're unmuted if you want to go ahead.
Am I unmuted?
You're on. Okay, go.
Okay. Yeah, I want to clarify it for my own, for myself. The issue of criticality in reactors or in spent fuel pools. I understand that to mean that fission takes place when you don't want it. Is it possible to create a nuclear explosion in a reactor or a fuel pool? Or are we only talking about explosions from nitrogen or some other gas?
Oh, okay. In a reactor, you want criticality. That's its entire purpose. The configuration of a reactor is different than that of a bomb. It is theoretically possible to make a reactor explode violently if you shut off all the safety valves somehow and pulled all the rods out, you would have a violent explosion. That's it's hard to imagine how that actually would be done. Safety valves typically don't have closure valves, stop valves on them. The sort of explosions you're worried about are the kind that we saw at Fukushima. Hydrogen explosions and in some instances steam explosions where molten coal material contacts water. So that's a quick answer. It can get complicated if you go further.
Did that answer it, Vic?
Well, I think Gordon. I think he was also asking when you talk about criticality in the fuel pool, what does that involve and
It's possible. It's unlikely. It would be self-limiting in that you'd get a burst of steam, and that burst would push the assemblies apart. So I would not anticipate a violent explosion.
And then the big danger is that the radioactivity that's in this fuel, which as we described earlier is the hottest part of the whole nuclear fuel chain, would be liberated through the release, the explosion, the plumes, the radioactivity getting out into the...
All of this pales into insignificance compared to the fire issue. Pool 4 at Fukushima came very close to catching fire, and if the wind had been towards Tokyo, they would have had 35 million people permanently relocating. That everything else pales into insignificance compared to that.
How long does it take a regular drum or barrel to corrode, and are they still used for storage? It's a question from Kimberly Huey.
When you're referring to barrels, are you talking about the canisters, or are you talking like the barrels at WIP? Is sharp of the canisters?
The question was written in, and it sounds like a regular drum or barrel, not necessarily the ones for irradiated fuel storage, but regular barrels and drums. Do you know about that?
Those are very thin metal, thin steel, and it depends on what's corroding them, how long they're going to last. When they were developing WIP, they used thin barrels there. They realized they were putting them in a salt environment, and rather than requiring something better, they said, well, we know they're not going to maybe last more than 10 years. They consciously decided that, but that it wouldn't matter. It was something like 10 or 15 years. And just to follow through on that, at WIP, you had a canister explode there, and they blamed it on kitty litter, but the reality is various labs have been using sawdust to sop up the liquid nuclear material and put them in those cans. So I even have a document from the scientists who were evaluating the impact of using organic materials. Hopefully that helps answer the question. While I'm on it, Hanford has tanks, and they're leaking, even the double wall tanks, and they have the same problem. They cannot adequately inspect them or monitor them or maintain it, prevent a leak, and they're using thin metal. It's not stainless steel, all of it. So we need to raise the standards for those other sites too to meet those basic minimum requirements you'd expect in a car.
Okay, next question is from Kevin to Donna. Those very short-term guarantees, warranties that Holtec was willing to make regarding dry cask storage at San Onofre, didn't the state decision makers see the disparities between that and the decades or centuries or longer of on-site storage, not to mention the million-year hazard that EPA has acknowledged
The Coastal Commission attorneys, the CPUC says they don't have jurisdiction. That's NRC jurisdiction. That was the answer from them.
Okay. The next question, can you scroll down? This is from Jan Boudart. Thanks for all this information and the work that you're doing. Question, the water in the spent irradiated fuel pool is borated, is it not? The truck by Unit 4 pool at Fukushima Daiichi must be spraying fresh or salty water. Please clarify the specs about the water in the fuel pool and what it would be replaced with in the event of an emergency. Is it true that TEPCO rarely or never mentioned the dangers at Unit 4? Are its problems more secret than Units 1, 2, and 3? Did you get all that?
Yeah, again, I repeat the point I made just a little while back, that criticality in a spent fuel pool is a physically possible thing. The borated water is there to prevent the possibility of criticality. From the point of view of radiological impact, the fire is far more significant. And so any water of any kind that could have been got into the Unit 4 pool should have been put in. And I don't know offhand if that fire truck was pumping seawater or fresh water, but it doesn't really matter. If I'd been running that operation, I'd have used any water I could have got my hands on. So it's it's a scale issue in terms of hazard. I hope that clarifies.
Fuel pool fires. The next question is from Michelle Lee. Dr. Thompson, thank you for your presentation and the work you've done on Indian Point. I'm curious to hear your thoughts about the time to potential spent fuel pool fire under two scenarios. One, earthquake triggering collapse of a spent fuel pool into the pool. Spent fuel pool roof into the pool. And two, spent fuel pool fire risk if a small private plane laden with explosives did a kamikaze type strike into the roof of one of the Indian Point pools.
I showed in my slide deck the severe reference case. That's where there is residual water at the base of the pool covering the bottom of the fuel assemblies. That's the case that you need to avoid at all costs. That's when your fire starts. And there are various circumstances that could put you into that situation. When you're in that situation, there's an ignition delay time. And I showed a table that for 3-year-old fuel, it's about a day. So if you've gotten your pool into this situation by whatever means, and you can get to it with fire hoses and put enough water in to refill it, then that's a recoverable situation. And at Fukushima, they were saved partly by luck, which was inward leakage, and partly they eventually got their act together and they brought in the concrete pumping truck. It was a close-run thing, and the two initiating events that we just described, the earthquake and the aerial attack, could prevent that recovery option.
Thanks. How does the panel anticipate DOE consent process for centralized interim storage or Nuclear Regulatory Commission licensing of the Waste Control Specialists WCS facility in Texas proceeding under the incoming Trump administration? That's from Greg Levine. Anybody?
Do you want me to take? I can take that. This is Donna. Well, the NRC, I don't think has ever not approved a facility. So the one in Utah, they approved that one too. It never happened because the state stopped it. So I'm assuming eventually the NRC will license those, but you still have the transportation issues. You still are going to have lawsuits. I'd like to hold out some hope that if we could get to somebody in the Trump administration high enough up and let them know that they could lose. Well, I guess they wouldn't lose Manhattan if it's there, but if they can be educated and believe the problems with these canisters, maybe we can turn this around a little bit. And it may be optimistic, but it's definitely worth the fight. So, and there's lots of problems with those interim facilities. I actually wrote to the governor of New Mexico and talked to their staff and pointed out the problems, but I didn't get anywhere, with their staff. They're just kind of ignoring it. So, anyway, so I think that lawsuits or anything we can do to slow it down, but given their track record, the NRC eventually approved anything.
To Gordon, can you address defenses against attacks on dry casks to prevent zirconium ignition, a la robust storage in 2003? That's from Kevin Camps.
Sure. The thick cask is better, as Donna said, from the point of view of long-term durability and inspectability. It's also better from the perspective of attack. And Donna quite rightly pointed out that in other countries, Germany especially, that they use thick-walled casks stored inside buildings. Those buildings in Germany are specifically designed against a design basis threat, which they don't disclose, but it's a non-trivial threat. There are some plants in Germany where the dry casks are in tunnels. So I'd recommend A, thick-walled dry casks, and B, external protection of some kind, which could be a building, a tunnel, or possibly a bermed type structure. There are various ways of going about it. One critical thing to remember is that you're at high risk, societal risk, of creating a repository by default, and that's the problem with tunnels. Out of sight, out of mind. So in terms of responsibility to future generations, there's an argument for having these, whatever structure, protective structure you put in place, visible. So it can't be just wished away and ignored.
Can you comment on how, let's see, this is, can you comment / characterize partial versus total fuel pool fire?
The terms partial and total are more often used in terms of the water loss. A paradoxical problem, a paradox about pool fires is that partial water loss is more dangerous than total water loss. And I have a picture there of slide 4 to show why that's the case. If a pool fire begins, it might or might not spread across all of the fuel in the pool. That'll depend on various factors, including whether the pool is packed full. So the fraction of the cesium that's released could range anywhere from a low fraction up to almost 100%.
Okay.
Okay, and the next question is for Donna from Linda Lewison. Can you comment on how you would recommend using a fuel pool in case of a dry cask leak? What about other solutions?
Other solutions? I'm not aware. Oh, I'm not aware of any other solutions. I was somebody who's been in the business a long time said the way you would want to put unload a canister would be preferably put it in an empty pool, so you don't risk contaminating other things. And there needs to be some technical analysis done on that because I don't think it's ever been done. So I'd have to defer to somebody that has more expertise on that area for the issues. In terms of alternatives, the vendors are telling everybody, including the DOE, that, oh, if you've got a leaking canister, you can just put it inside a thick cask of some sort of overpack. But what they don't mention is that cask can overheat. That fuel's still hot, and I don't know even how they would get close to it if it's, if, as Dr. Holtec says, it would be releasing millions of curies of radiation. So I'm not sure, did I answer Linda's question or did I miss what she was getting at?
Well, I think one of the questions that we have is whether, Linda said yes, you did. Okay. All right, so we'll move on. We've got 2 more questions and we've got 1 more minute. Greg Levine is asking, does Donna want the San Onofre nuclear generating station irradiated fuel moved off-site entirely, like to another operating power plant, or just to a better place on or near site and in better casks or hardened on-site storage? That's for Donna.
What I have been what I've been fighting for and is getting better on-site storage. I was hoping that we could kind of set the standard here. I don't believe it's reasonable to take thin canisters and dump them on somebody else, and there's transportation risks and everything. It would be good if they were located further away from they're only like 100 feet from the cliff. The issue, I don't know if you've heard, there's actually Sierra Club's old policy, I think it's still in effect, that said that the only time you want to move fuel somewhere else is if you have some kind of imminent danger where it's at, then only move it to the nearest operating reactor, which in our case would be Palo Verde. But it definitely needs to be on higher ground and better containers. Now, the majority of the community here will just want it out of here. And Edison has been taking advantage of that and getting people putting their energy into getting it out of here. I don't think it's going to go anywhere anyway, not before we have a problem. But, you know, people want to believe what they want to believe. So it's created a problem here. In fact, the only way I could get a city council resolution passed here was to say, hey, we didn't sign up for the waste, we don't want it here. I just avoid saying, you know, move it to a consolidated site. I don't think that's a good solution. But I just say a general statement, we didn't sign up to be a nuclear waste dump, we want it out of here, and then you go into, and while it's here, it needs to meet these requirements. So that's kind of a way I've kind of bridged it, not supporting the consolidated interim site, but at the same time acknowledging that we didn't sign up to be a permanent waste dump. So anyway, so that's kind of how I've dealt with it here. Hope that answers the question.
Yeah, and we've got one more comment here.
Oh, there's one more thing I want to mention. The NRDC, Jeff Fettis, he mentioned that the most economical option as an alternative to consolidated interim storage is to move it to the nearest operating reactor, because then you minimize the overhead. So if the industry was, or the administration is trying to make the case that the consolidated interim storage site is the cheapest option, it really isn't. You know, so if you're trying to make a cost argument, you know, that was something you mentioned, that would be the cheapest economical option to move it to the nearest operating reactor. The DOE has totally ignored the infrastructure risk. They've only said infrastructure is problematic, but they haven't really addressed it. So that's a whole other deal. The other thing you'll hear is, well, the Navy moves their waste and it's not a problem, where ours is totally different. So that would be a whole nother session, but just be aware of that too. That's what you're going to hear.
Okay, so the last comment is from Kevin, following up on Greg Levine's question. Waste Control Specialists, or WCS's license application to the Nuclear Regulatory Commission is illegal under the terms of the Nuclear Waste Policy Act as amended. The Nuclear Regulatory Commission is violating the law simply by proceeding with the review of the WCS license application, such as undertaking the environmental impact statement. NRC, a rogue agency violating the law, has to be brought to heel, be it through legal action, as Donna mentioned, or by congressional oversight. And on that note, we will, unless anyone wanted to comment on that, we will draw this session to a close. Did either of you want to make a comment on that last comment?
I have a different statement. I look forward to seeing everyone in Chicago.
Fabulous. Thank you all for...
Okay, I just real quick, what WCS said, because in an NRC meeting I listened to, the NRC asked who was going to be the licensee, and WCS said unless the DOE is the licensee that they wouldn't go forward with the project. That's what they said at the time. So that's why there's legislation pending to basically try to get DOE to be the owner of this, or, you know, somehow do it. So we need to stop that legislation. We need to educate on what's really happening with that legislation. That's a whole other project and a whole other presentation.
All right. Thank you, Gordon and Donna, and thank you all of the people who joined in to participate, ask questions, listened in, and we do hope to see you all the first weekend of December in Chicago.